When we go to determine the oxidation number of atoms that are within a molecule or an ion, there's two approaches that we can commonly use. One I describe in another video where I compare it to formal charge, and I mentioned that oxidation number is just like doing formal charge, except that we assume that every bond is being dealt with in a completely ionic fashion. And we see a summary for that here that I'll compare to in just a moment. And water is the one that I used in that other video, so it's worth looking at that one alongside of this video in case you haven't seen them both. Now, the other approach is to use a rules-based approach. And the rules-based approach is much faster because we don't have to draw a Lewis structure. And we can commonly go through an entire ion or molecule without actually drawing out the structure for it. Now let's take a look at what those guidelines are and see if they give us the same answer as the Lewis structure-based approach. Now the first step of that approach is to say that if the atom is in its elemental form, the oxidation number will be 0. And when we say elemental form, we're describing the really common ones you can find. So examples of elemental forms are things like H2, O2, iron solid with no charge, same with all the other metals for that. Sulfur is an S8 for its elemental form, and there's a few others out there. There is another video that we have in the channel for elemental forms, and you can find that if you'd like to see it. And I also have that in our Canvas page as well. Now, that means that the atom will be 0, but we're going to have to go through the whole molecule to find out the rest of the atom types. Now, the second line is going to say if it's a monatomic ion, then the oxidation number will equal the total ion charge. In other words, this is the thing we already knew. If we have Fe2+, its oxidation number is 2. If we had iron 3+, its oxidation number is 3. If I have O double minus, it's an oxidation number of -2. So for monatomic ions, oxidation number is the same as the charge. Now when you have a molecule or a polyatomic ion, the sum of all of your oxidation numbers has to equal the sum of the charges. And of course, if there is no charge, that means it's got to equal 0. So for molecules and for neutral formula units, the sum of the oxidation numbers must be 0. And for a polyatomic ion, it all has to add up to be the overall charge. Because what we're doing with oxidation number is we're predicting where the charges will be in an ion when we're making the assumption that all the bonds are going to behave ionically. Now, the fourth one is since group 1A and 2A are always going to be +1 or +2 for their charge, that will be their oxidation number. So everything in hydrogen's column over in column 1 will be a +1 oxidation number. Everything in the same column as calcium will be a +2 oxidation number. Now, there's a couple of other rules that the textbook will mention, like oxygen will always end up being O2-, and so its oxidation number will always be a -2, unless it's in a peroxide. Now, I'll show the peroxide example here in just a moment. But notice, if we use the rules that we have down here, none of these are in their elemental form. We don't have a monatomic ion. The molecule, the sum of all of our charges have to end up being 0. So we'll check. I've already assigned it to be a +1 and a -2. I have 2 +1s. -2 gives me an overall charge of 0. So that rule has been fulfilled. For our group 1, hydrogen will be a +1. Hydrogen is an exception in the sense it can also be a -1. Remember when we learned our nomenclature, we said there can be H+, which is a proton, or we can have the hydride ion, where it's picked up one electron and it has a -1 charge. So there's a lot of rules you can use for oxidation number. And so yeah, this one will match up with the exact same oxidation numbers we found by using the Lewis structure method. So all of these are self-consistent. Now, if the problem asks you to determine an oxidation number, for example, if we're talking about rust, Fe2O3, and it asks, what is the oxidation number of iron? What you'll do is you'll work it backwards. I see that the overall charge on this is a 0. I know that oxygen will always be a -2, and I have 3 of them. And I'll be adding that to some unknown charge for iron. I figured this one out and I say, okay, this is a -6. To make that be 0, My question mark here has to be a plus 6 coming from the irons. So if the overall effect of iron has to be plus 6, that means that each of these 2 iron atoms have to be a plus 3, and I have 2 of them. So that's how we could determine the oxidation number the long way around using these rules. Now notice, this would be hard to draw a Lewis structure for. That's why it's important that you also memorize the rules that are here and in your textbook so that you can use the shortcut from the rules. But I want us to be able to see it with the Lewis structure approach as well, so that you know exactly what is lying underneath the rules. Because pointless rules never made sense for me. I want them to have a physical underlying reason.